Example 3 says the value of a truck bought new for $28,000 decreases at 9.5% each year. Write an exponential function to show the truck's depreciation. So we're trying to write a function, which means once again we're going to be using this model here. And this time, because it's depreciation or decreasing, we're going to do an exponential decay, which means it's going to be 1 minus r instead of 1 plus r, like we saw in the growth function in example 2. So we have a of t equals our initial amount. So the truck was purchased for $28,000. And I have 1 minus, remember our percentage must be represented as a decimal. So take the decimal point and move it left 2 units, making it 0.095 to the power of t. That means our function is a of t equals 28,000 times 0.905 to the power of t. Notice how the base here is between 0 and 1, which is why I said it was a decay. And the base here was greater than 1, which shows it was a growth. Again, this function is important because now we can estimate the value of the truck. So let's say after 10 years, the person who purchased the truck would want to sell it. He can estimate the value for resale. So if he wanted, after 10 years, we would plug in 10 for t. So that would be 28,000 times 0.905 to the 10th power. So when you're plugging it in your calculator, I have 28,000 times 0.905. To raise it to the power, I just hit this little caret button right here. So caret. If the power were negative, you'd want to put the power in parentheses, but because it's positive, I don't have to. You can if you want to. Parentheses 10. So that means in 10 years, when he goes to resell it, it will only be worth $10,319 and about 15 cents. So that's an approximation. Now we're going to take a look at graphing exponential functions. We already did this on the first page when we graphed f of x equals 2 to the power of x. So we're just going to follow each of those steps that's listed above these examples. A is to create a t-chart using -2 through +2. B is to actually graph the function. C is identify if it's a growth or decay. And then D is to state the domain and range for the function. So for number 2, I'm going to create a table from -2 to +2. And for the y column, I just need to plug in my x value into the function. 1/3 to the -2. 1/3 to the -1. 1/3 to the 0 power. 1/3 to the first power. And 1/3 squared. What's easiest for you should be the last 3. Anything to the 0 power, remember I told you, is 1. Anything to the first power is just itself, so I have 1/3. And then when I have 1/3 squared, because I have division here, I can distribute the power to each of those terms. So really it's 1 squared over 3 squared, or 1 over 9. We're going to use the same idea of distributing the power for the negative exponents. So I have 1 to the -2 over 3 to the -2, and 1 to the -1 over 3 to the -1. Remember, I had mentioned already that when we have a negative exponent, we need to move it. So if I have a negative exponent in the numerator, I need to move it down into the denominator. So I have 1 squared in the denominator now. The act of moving it made the exponent positive. And if it's in the denominator, I need to move it up to the numerator. So 3 squared is now in the numerator. Again, the act of moving it is what made it positive. So really, I have 3 squared over 1 squared, or 9 over 1, which is just 9. Okay. Same thing, I need to move it down or up depending on the power. So 1 to the first power is in the denominator now, and 3 to the first power is in the numerator, which gives me 3 over 1, or just 3. I'm going to use a separate sheet of paper for my graphing because it took up quite a bit of space. So we're just going to use these points. I'm going to pause it and draw my graph. I'd like you to do the same. Here's my graph of the function. You can see that after plotting the points, I drew a curve connecting those points. And also keep in mind, your graph should not cross this x-axis because there's what's called an asymptote on that x-axis. So it's going to get really, really close to 0, but never quite touch it. Looking at this function, I can tell that as x increases, the function is actually decreasing. It's getting closer and closer to 0. So this is an exponential decay. It also asks for us to identify the domain and range. The domain should be easy. It's always going to be all real numbers. It's going to the left, it's going to the right. But the range could change, so we just need to keep that in mind. Should always be down to up. So the lowest is 0, and that's going to go up forever towards infinity. Both of those would be parentheses because they're not included. Looking at number 5, let's start by creating our table. Once again, we're going to go from -2 to +2. To get the y column, we just plug these x values into our function. So I have a -2 to the -2 power, a -2 to the -1 power, a -2 to the 0 power, a -2 to the first power, a -2 being squared. So whenever we have an a value, which is what we have here, a is -1, you need to keep that a where it is. The power only goes to the base b. So this negative is not going to be affected at all by whatever 2 to the power is. Okay, we need to keep it there. If it were a number like what you're going to see in number 3, you would find what 2 to the power is and then multiply it by 1/2. Because technically what we're doing here is we're going to take 2 to the power and we're going to multiply it by -1. Okay, so here I have a -2 to the -2 power. So because it's negative, I need to move it down, giving me 1 over 2 squared, or a -1/4. Same thing here, I had a negative exponent, so I need to move it down. I have a -1 over 2 to the first power, or a -1/2. Anything to the 0 power is 1, so I have a -1. Okay, anything to the first power itself, so I have a -2. 2 squared is 4, so 4 times -1 is a -4. I'd like you to pause the video and draw your graph. Here's my graph. Now, part C is actually pretty tricky because it says we need to identify if it's a growth or decay. This graph actually is showing you a growth function. Now I know it's kind of confusing because it's going down forever, right? Well, there's 2 types of growth and decay functions. There's an increasing one, where it's going up towards positive, and then there's a decreasing, which goes towards a negative. The best way that I can can describe it to you is if it's an increasing growth function, then it's growing at an exponential rate in a positive value. So like the guitar problem where it was purchased for $12,000 and the value was increasing. Well, same thing with, let's say, a growth situation like this one, where it's growing exponentially. The amount is growing, but in a negative direction, so negative values. Think about debt. So when you take out a student loan for, let's say, $10,000 when you go to college, you don't have to just pay back $10,000. There's an interest there, right? And that amount is only going to grow if you're not making payments on it. So it will be growing exponentially, but it would have negative values. So this is a decreasing exponential growth function. It's still growing as we move to the right, as the x values increase. So that one was a little bit of a tricky one. The thing we have to do now is domain and range. Domain is always going to be all real numbers, once again, but range here is a bit different. Remember, range is down to up. So this goes down forever towards negative infinity. And the highest it can go is 0, because remember, we're supposed to have an asymptote here. It can't cross that x-axis. So that means it's going to be a parenthesis. Number 6 is the last one I'm going to do with you, and then you're going to try the other problems. Once again, let's create a table going from -2 to +2. So now I'm just going to plug in the values. Now be careful here because it's 3 to the negative x. So it's 3 to the negative -2, 3 to the negative -1, 3 to the negative 0, 3 to the negative 1, and 3 to the negative 2. So really, when we have two negatives, that makes a positive. So this is 3 squared, or 9. This is 3 to the first power, which is just 3. Negative 0 doesn't really affect it. It's still 3 to the 0, so that's just 1. 3 to the -1, because it's a negative exponent, we need to move it down, making it 1 over 3 to the first power, or 1/3. And then again, negative exponent, bring it down, we have 1 over 3 squared, or 1/9. Pause the video and draw your graph. So number 6 is another tricky one, because initially when we look at it, the base is 3, so we would think it would be a growth, right? But as x increases, the number or the function itself is decreasing. So this is actually an exponential decay function. So we need to ask ourselves, why is this so? Why does the base look like it's a 3, but it's actually a decay? Well, that's because the function was 3 to the negative x. We know if we have a negative exponent, we need to move it down. So really, it's 1 over 3 to the power of x. So the base is 1/3, because 1 to any power, so if I wanted to say 1 to the x power, I mean, it's just going to be 1 always. So I could also rewrite it as 1/3 x. The base is between 0 and 1. It's a decay. It makes sense. Domain is all real numbers. Range would be from 0 to positive infinity. I would now like you to try 1, 3, and 4. Hit play when you're ready to check your answers. Feel free to pause it so you can check your answers for 1 and 4. I know you can't see it on yours, but number 4 is domain all real numbers, range 0 to infinity. And then here's number 3. Feel free to pause it and check your answers. There's my graph for number 3 right above.